Alright, I'm going to walk you through the process of solving problem 9.118, and I'm only going to show you how to do part B. However, in order to get part B, you will need to find part A. Alright, so the problem says, use the molar diagram in figure 8-8E to determine for water vapor at 500 pounds force per inch squared, 600 degrees Fahrenheit, and 1,000 feet per second, find the stagnation enthalpy in BTUs per pound, the stagnation temperature in degrees Fahrenheit, and the stagnation pressure in pounds force inch squared. So again, we only need to find the temperature. So the first thing you may be asking is, what is a molar diagram? Well, a molar diagram is an entropy enthalpy graph, and the different, or plot I guess would be more accurate, and the different lines on here represent different things. So for stuff underneath the vapor dome, we've got lines of constant quality in this area. For the kind of the horizontal lines, so these are lines of constant temperature. And then the vertical lines going up are lines like these, and over here are lines of constant pressure. So the first thing we want to do is we want to find the stagnation enthalpy. Now, on this molar diagram, we need to look at the points for a pressure of 500 pounds force and a temperature of 600 degrees Fahrenheit. So we're going to start with temperature. So we're going to find the 600 degree temperature line. Let me make that pretty. So the 600 degree temperature line is this one. So now we're going to need to find the pressure line. So the pressure of 500 pounds force per square inch is this line. And where they cross, that's where we want to get the first part of our enthalpy term. I'll show you what it's used for in a second. So right where they cross, oops, didn't change it over. Right where they cross, right here, we have an enthalpy of about, just giving a rough eyeball, we'll call it 290. We'll call it 1300 for the sake of rounding. These graphs are very, it's a lot of eyeballing, a lot of guessing and hand waving. So we'll call it an enthalpy, HO. This is not the stagnation enthalpy. Sorry, not HO, just H. An H of 13. Sorry, can't write. Yeah, 1300 TU. And we'll also need the entropy. So looking up at the entropy, we'll call that 1.55. So, go away. S equals 1.55 BTU LB degrees Rankine. Alright, so now that we've got that, we need to bring out our stagnation enthalpy equation. So I'm going to move up here for a minute. So stagnation enthalpy, as y'all all should know, HO equals H plus V squared over 2. Now, this is showing that isentropically, all the energy of motion is basically turned into enthalpy. It's the easiest explanation. And because this is in English units, it's a little bit of a hairy problem. So we're gonna just go straight over. So we have our starting enthalpy, of 1300. I'm gonna keep for the sake of cleanliness, I'm gonna keep the units out of here. So pay attention. So we were given 1,000 feet per second up here, 1,000 feet per second. So 1,000 squared over 2 as per the equation. But because it's in English units, doesn't start pretty, we have to get gravity out of the way. So 32.2 for English. And we also have to do the conversion of pounds force into BTU. And so that's another 1/778. So when you do that, you're going to get something right around 1320. Now again, this is not exact because you are using, it was requested that we use the chart rather than the other equations that can be used to found this. So now we want the stagnation temperatures with the stagnation temperature with our new stagnation enthalpy. So we're going to go back to our chart and we're going to find the line that's at near in and around the 1320 BTUs per pound. So let me get a green highlighter. So 1320 is right about halfway between the 1300 and the 1350, so right in this area. So we'll just draw as straight across as possible on a tablet screen. So now we're looking for our, and then additionally the entropy does not change. That's the kind of the y coordinate of this. So it's still at 1.55. So we'll go up here and we'll come down. That's not very straight. Anyway, 1.55. So now we can see that it crosses, let me get the marker back out. So now we can see that the marker crosses right about there. So we'll call that about 650 degrees Fahrenheit. So TO. Now, for those of you that have access to the solutions manual or know where to find the answer, these numbers are a little bit differently because I eyeballed it. If you were to check with the solutions manual, you would end up with a stagnation enthalpy of 317.9 BTU per pound, and that would change your stagnation temperature to 645 degrees Fahrenheit. So again, we're only a little bit off, and it shouldn't be much of a big deal. The key, though, is that the process is correct, and that's all that matters. So hope that helps you all out.